Today, we will discuss what is involved in biaxial testing of materials. Whenever we encounter a new material, first we want to explore the physical properties of it. How does it feel? What does it look like? But we also want to know how stiff a material is. One approach is to stretch it along one direction, also known as uniaxial stretching. But it is also important to understand the difference between isotropic and anisotropic materials. A balloon, for example, if I take a piece of it, I can stretch it one way. And because it is isotropic, having the same property in any direction, I can stretch it the other way and expect the material to stretch the same amount. Wood, on the other hand, is not isotropic. Take this 2x4. If I take a piece of this wood, I can closely see wooden fibers predominantly align in one direction. If I stretch it up and down, it may deform some distance. If I stretch it sideways or orthogonal to the direction of the fibers, I can expect it to deform differently. Stretching it only one way does not capture what the material property could be in the other direction. Hence, biaxial testing comes in handy. In a real-world application, imagine we want to test the properties of the tissues in the heart. In this example, we are interested in discovering how stiff a heart valve is. Heart valves are composed of leaflets. Together, they close and keep blood flowing in one direction. What kind of material structure can we expect to see from this if we apply a load? Here is an isolated heart valve that was dissected. Although hard to see, a pattern of small fibers appear horizontally. Not much structure is obvious going in a vertical direction. In our experimental approach, we trim the tissue to a smaller size and attach hooks and surface markers, which we can then track to quantify tissue deformation. We then proceed to mount it and stretch. Because of the present anisotropy of the specimen, a biaxial tensile machine is a great tool to use. Here is a render of the biaxial tensile machine. As the name suggests, we apply tension on two axes. We have axis 1, which has a pulling mechanism, and directly opposed from it is a load cell. This allows us to measure how much force we're applying on this axis. Likewise, 90 degrees apart, we have axis 2 with a very similar setup. The picture on the right shows the experimental setup. We have our tissue with the fish lines that have been attached to the pulling arms on one side, and then the other go around the load cell, as previously discussed, to measure how much load we're applying. If we look at our graph with real data, we notice that as the stress or load increases, the data in blue has undergone more strain or deformation than compared to the data in red. This tells us that the other direction, shown in red, is stiffer. Comparing it to the previous image to make more sense, if we have our bundle of fibers aligned horizontally in the red direction, I can pull in the blue direction and spread those fibers apart much more easily than if I stretch it along the red direction. This is why the red direction is stiffer. Think about the strings on a guitar. It is much stiffer to stretch the guitar strings along the direction of the strings than it will be to stretch the strings apart from each other. In step 1, we have learned what the difference is between isotropic and anisotropic materials, having properties that vary in different directions. We then understand why a machine that measures stretch characteristics in not one, but two separate directions is useful. We used a real-world application where biaxial testing is necessary, such as studying the material properties of the heart valves. And finally, we analyze the load versus deformation graph. Does one direction stretch differently than another? If so, we have captured anisotropy of the material.